of the most powerful concepts when analyzing a linear system is the Laplace transforms. And these are looking at systems in the frequency domain when you're dealing with continuous time systems. When you're dealing with discrete time systems, you deal with Z transforms, which is related to the Laplace transform. But here we're just going to focus our attention to Laplace transforms. Some of the topics we're going to talk about are the Laplace transform in terms of a pole zero diagram. We're going to take a look at the inverse Laplace transform, and that's just basically what involves is going from the frequency domain to the time domain, whereas the Laplace transform involves going from the time domain to the frequency domain. Why do you want to do that? Well, sometimes it's easier to operate in one domain or the other. So let's say in the time domain there's a complicated integral like the convolution, and you want to go back in the frequency domain where it just involves simple algebraic calculations. We also have the circuit response using the Laplace transform. This will be an example in which we look at a first and second order circuit. And then finally we're going to conclude with the initial and final value theorems of a response, system response. Here's a block diagram. This is coming from a circuit analysis book, but is it general, applies to any system, mechanical system, thermal system, aero-mechanical system, any type of system you can think of. The Laplace transform can be used to describe it if it's linear. So here we begin with a linear circuit. Circuit can be described in terms of a differential equation. We can use many techniques, classical techniques, to get the output response of a system. What I mean by the output response, we put in a particular input and we can be able to predict the behavior of the system based on its output. So here, sometimes doing this part of the diagram in time domain gets kind of complicated, so sometimes it's easier to go to the Laplace transform, symbolized by this script L, in which we can do an algebraic equation, do algebraic techniques, get the response. So all this is operated what we say in the Laplace domain or the frequency domain description right here. And then once you got the output description in terms of the frequency domain, then we go back to the time domain via the inverse Laplace transform. So going from the time domain to the frequency domain and then going back. So you can go back and forth by using these linear operators called the Laplace transform and the inverse transform. So what we're going to do is take a look at some examples. But before we look in these three examples, we'll take a look at the definition of the Laplace transform. So the definition of the Laplace transform is that here's a regular signal, let's say the output of a system, could be also the input of a system, where we transform it in the frequency domain. Here it's a function of time, here's a function of this S variable called it describes a variable in the complex plane. We'll describe that further. So here's going from an integral from 0 to infinity, f of t multiplied by e to the minus st. Okay, shown here, dt. So that's a time domain description, and this is the S domain or frequency domain description. Signal waveforms and transforms. Here's example 1. We want to show that the Laplace transform of a step input looks, let's see if I have an example of that. Okay, step input looks like this. Here's a function of time. Okay, and the step input, there's 0 before time t equals 0, so right here that's the 0, the origin, and that's time. And then our single axis, so we'll call this f of t. So no input, and out pops a step. Alright, so that's what we mean by the step input right there. So let me go back to the pointer. And so here's f of s, f of t, our definition. So it's basically a unit step with a height of 1. Substitute right here. It exists from 0 to infinity. 0 to infinity e to the minus st, since u of t is 1 from 0 to infinity. Okay, evaluating the integral, you can use the tables. So e to the minus st divided by s with a minus sign in front because of the minus sign of e up here. Evaluated from 0 to infinity. Substituting s for, this is our definition, consists of a real part and imaginary part. The real part, you can think of it as a decaying exponential, and the imaginary part is an oscillation like a sine and cosine function. So replacing the s with this type of function, you have that. Okay? So anyway, so s to the minus infinity, evaluating the upper limit, then the lower limit, yields the following result, or 1 over s. So in other words, whenever you see this function in the time domain, this is how it's described in the frequency domain. Example 2. Show that the Laplace transform of an exponential given as follows, where we multiply by the step, but that's just telling you that the exponential exists only from 0 to infinity. There's no negative term, because we just saw that earlier, what a step function is. So we're going to evaluate it from 0 to infinity. We'll want to show that given alpha here, in this case, greater than 0, is equal to this. Okay, we're evaluating from 0 to infinity as a result of this step function. Separating, substituting e to the minus st in f of t here. Since these are common base, we can add these exponentials. And you can see it's in the form similar to the previous one, except of the s we have s plus alpha. So doing the same type of integration. The s plus alpha goes down in the denominator with the same exponential here, evaluated at infinity to 0. 0 minus 1 over s plus alpha yields 1 over s plus alpha. Now in the system, you can think of this exponential right here. In the previous example, in the first example, there was no exponential, but you can think of it as alpha equals 0. So if alpha equals 0, we get 1 over s. Alright? So we can think of the integral as a pole or particular characteristic of the system, and in this case, the pole here is at alpha. Okay? And we'll see this pole is a key characteristic in governing the stability of the system.